Hello, my name is Joali Delgado Alvarez, and today I will present our work entitled GPA for Dummies, Understanding How Lattice Distortions Affect Geometric Phase Analysis. Geometric phase analysis, or GPA, is a widely used technique for extracting quantitative structural information from high-resolution TEM or STEM images. It transforms these images into maps of atomic displacement, strain, lattice rotation, and dilation. However, GPA maps are not always easy to interpret. Some lattice distortions are too subtle to identify through direct visual inspection, and some apparent features in the maps can be caused by image processing choices rather than by real structural changes. Therefore, the objective of this work was to evaluate the robustness of GPA and understand how different predefined lattice distortions affect the resulting displacement, strain, rotation, and dilation maps. The theoretical basis of GPA is the relationship between the geometric phase and the local displacement field. For a selected reciprocal lattice vector, the geometric phase is proportional to the projection of the displacement field along that vector. By selecting two non-collinear reciprocal lattice vectors, we can reconstruct the two-dimensional displacement field. The spatial derivatives of this displacement field are then used to calculate the strain tensor, lattice rotation, and mean dilation. In simple terms, GPA converts small changes in atomic positions into quantitative maps that describe how the crystal lattice is locally deformed. To systematically study the GPA response, we evaluated 9 idealized systems. This included displacement along the x and y directions, double displacement along x, simultaneous displacement along x and y, rotations about the 3 Cartesian axes, and displacements with linear and nonlinear spatial gradients. Our methodology consisted of 3 main stages. First, the atomic structures and controlled lattice distortions were generated using Materials Studio. This allowed us to define exactly which deformation was introduced into each system. Second, simulated out-of-STEM images were produced using prismatic and AV-TEM. These simulations provided images with non-structural modifications, which is essential for comparing the imposed distortion with the GPA response. Finally, the images were analyzed in digital micrograph using a GPA plugin. 2 reciprocal lattice reflections were selected from the Fourier transform, and these reflections were used to calculate the geometric phases, displacement components, strain components, lattice rotation, and dilation. The representative results, shown in the center of the poster, correspond to displacement in both x and y, rotation about the y-axis, and displacement with a nonlinear gradient. For each case, we show the normal strain components epsilon xx and epsilon yy, the shear strain epsilon xy, the in-plane rotation, and the mean dilation. We also include 2 geometric phase maps, the reconstructed displacement components ux and uy, the original simulated image, and its Fourier transform. For the combined displacement in x and y, the GPA maps detect changes in both displacement components. This demonstrates that GPA can distinguish the directional contribution of a 2-dimensional lattice displacement. For rotation about the y-axis, the deformation is projected onto the 2-dimensional STEM image. Consequently, the resulting GPA maps do not necessarily represent a simple uniform in-plane rotation. Instead, the response depends on how the three-dimensional rotation changes the projected atomic column positions and lattice spacing. The nonlinear gradient case produces a spatially varying response. Unlike a rigid translation, which mainly changes the phase, a displacement gradient produces measurable strain because the displacement changes from one region of the sample to another. This distinction is important. GPA measures local variations in displacement, not simply the absolute position of the lattice. These results also show that strong features frequently appear near the image boundaries. Such signals must be interpreted carefully because they may result from Fourier filtering, mask selection, periodicity assumptions, or other edge effects rather than from the intended lattice distortions. From this study, we conclude that GPA is a powerful tool for mapping lattice strain, dislocations, interfaces, and other structural variations. It provides quantitative information that may be difficult to obtain through direct inspection of the HRTEM or STEM images. Nevertheless, the interpretation of GPA maps strongly depends on crystallographic orientation, reference region selection, reciprocal lattice vector selection, system geometry, and image processing parameters. Controlled lattice distortions are therefore useful for understanding the physical meaning of the GPA response and for identifying its limitations. They provide a known reference that helps us distinguish genuine structural signals from numerical or experimental artifacts. Future work should include more complex geometries, interfaces, stronger strain gradients, and different crystallographic orientations. It will also be important to study experimental distortions such as the flyback effect, which occurs during STEM scanning and can produce artificial displacement or strain features in GPA maps. Overall, GPA should not be treated as an automatic strain measurement method. Reliable interpretation requires a combination of crystallographic knowledge, careful image processing, and comparison with controlled models or simulations. Thank you for your attention.